Episode 5, Pythagoras and the Music of the Spheres, Part 1. Welcome back to the Slumbering Musicologist. I'm delighted you've returned for another journey through the ancient foundations of Western music. Tonight, we venture into a realm where mathematics meets melody, where philosophy embraces harmony, and where the stars themselves were believed to sing. We're exploring the extraordinary ideas of Pythagoras and his vision of cosmic music, the music of the spheres. In our previous episodes, we've traveled through the musical worlds of ancient Mesopotamia, Egypt, and Greece. We've encountered the earliest written songs, temple rituals, and the sophisticated musical culture of classical Athens. Tonight, we turn our attention to one of the most influential figures in the history of music theory, a philosopher whose mathematical discoveries would shape how Western civilization understands sound itself. Pythagoras of Samos. Even if you know nothing else about ancient Greek philosophy, you likely remember his famous theorem about right triangles from your school days. But Pythagoras was far more than a mathematician. He was a mystic, a religious leader, a musical theorist, and a visionary who believed that numbers held the secret to understanding the universe. His ideas about music would echo through 25 centuries of Western thought, influencing everyone from Plato to Boethius, from medieval scholars to Renaissance scientists, from Johannes Kepler to modern composers. What makes Pythagoras particularly fascinating for our purposes is his radical proposition that music is not merely an art or an entertainment, but a fundamental principle of cosmic order. He believed that the same mathematical ratios that create pleasing musical intervals also govern the movements of the planets, the structure of the soul, and the very fabric of reality. In the Pythagorean worldview, the universe itself is musical, a great celestial symphony playing eternally, if only we had ears refined enough to hear it. Before we lose ourselves in the mathematical mysteries of ancient Greece, a gentle invitation. If you find these explorations of music history helpful for rest and reflection, I'd be grateful if you'd consider subscribing to the Slumbering Musicologist. New episodes arrive every Friday at 6 p.m. Greenwich Mean Time, each one offering another peaceful journey through the history of Western music. Feel free to leave this video playing as you drift towards sleep. The music and narration will continue, creating a gentle atmosphere for rest. To understand Pythagoras and his musical philosophy, we must first understand the world of 6th century Greece before the Common Era. This was an age of remarkable intellectual awakening, a time when Greek thinkers began asking fundamental questions about the nature of reality. What is the world made of? How can we know what is true? What principles govern the cosmos? These questions gave birth to what we now call philosophy, literally, the love of wisdom. Pythagoras was born around 570, before the Common Era, on the island of Samos in the eastern Aegean Sea. Samos was a prosperous place, strategically located at the crossroads of Greek and Near Eastern culture. The island's ruler, the tyrant Polycrates, was a patron of the arts and engineering, famous for commissioning an underground aqueduct that remains an engineering marvel. This was an environment where intellectual curiosity flourished. The Greek world of Pythagoras' youth was not the unified nation we might imagine. It was a constellation of independent city-states: Athens, Sparta, Corinth, Thebes, and hundreds of others spread across the Greek mainland, the islands of the Aegean, the coasts of Asia Minor, and eventually colonies stretching to Sicily and southern Italy. Each city maintained its own government, its own customs, its own musical traditions. Yet they shared a common language, common religious festivals, and an increasingly common cultural identity. This was the age of the lyric poets. Sappho of Lesbos had composed her passionate verses only a generation before Pythagoras' birth. Her contemporary Alcaeus sang of politics and wine. The poet Archilochus had revolutionized Greek verse by adapting traditional meters to personal expression. Music and poetry remained inseparable in Greek culture, Virtually all poetry was composed to be sung, accompanied by the lyre or the aulos, the double reed instrument we encountered in our previous episode. The political landscape was turbulent. Traditional aristocracies were giving way to new forms of government. In some cities, strong individuals called tyrants, not necessarily cruel, simply holding power outside traditional structures, took control. In others, oligarchies of wealthy citizens ruled. Athens was beginning its long evolution toward democracy, though that revolution still lay ahead. The resulting political instability drove many intellectuals to travel, to seek wisdom in foreign lands, to establish new communities based on philosophical principles rather than mere geography. Into this dynamic world, several remarkable thinkers were emerging with revolutionary ideas. Thales of Miletus proposed that water was the fundamental substance of all things. His student, Anaximander, suggested instead an infinite, undefined principle he called the apeiron. Anaximenes argued for air as the primary element. These Milesian philosophers were attempting something unprecedented, to explain the natural world through reason and observation rather than mythology. Heraclitus of Ephesus would soon declare that fire was the essential element and that everything flows in constant change. Xenophanes challenged traditional Greek religion, arguing that humans create gods in their own image. Parmenides would argue the opposite of Heraclitus, that change itself is an illusion and that only unchanging being is real. These were not idle speculations. These thinkers were laying the foundations for systematic philosophy, for science, for rational inquiry into the nature of existence. Pythagoras absorbed these intellectual currents. Ancient sources suggest he traveled widely in his youth, though we must be cautious with these accounts. Later writers love to embellish the biographies of famous philosophers. Nevertheless, tradition holds that Pythagoras journeyed to Egypt, where he may have encountered the mathematical knowledge and religious practices we explored in our third episode. He may have traveled to Phoenicia, to Babylon, even to Persia. Whether these journeys actually occurred, they reflect the international character of 6th century Greek intellectual life. What we know with greater certainty is that Pythagoras eventually left Samos, possibly fleeing the tyranny of Polycrates, possibly seeking a place to establish his philosophical school. Around 530, before the Common Era, he arrived in Croton, a Greek colony in southern Italy. Southern Italy and Sicily formed what Greeks called Magna Graecia, Greater Greece, a region of prosperous Greek settlements. Croton was known for its medical school and its athletic champions. Here, in this thriving colonial city, Pythagoras would establish his community and develop his revolutionary ideas about music, mathematics, and the cosmos. The Pythagorean community at Croton was unlike anything that had existed before. It was part philosophical school, part religious brotherhood, part political organization. Members followed strict rules of conduct. They observed dietary restrictions famously. Pythagoreans refused to eat beans, though scholars still debate the reason. They practiced communal ownership of property. They studied mathematics, music, and astronomy. They believed in the transmigration of souls, that, after death, the soul moves into another body. They maintained periods of silence, using the time for contemplation and internal examination. This was not merely an academy for abstract learning. The Pythagoreans sought to live according to their philosophical principles. They believed that through studying mathematics and music, they could purify the soul and achieve a higher understanding of reality. Music was central to this process. The Pythagoreans used musical performance as a form of spiritual exercise, a way of attuning the soul to cosmic harmony. The intellectual atmosphere of 6th century Greece created the perfect conditions for Pythagoras' synthesis of mathematics and music. Greeks had long recognized that music possessed mathematical characteristics. Instruments had specific numbers of strings, melodies followed patterns, rhythms divided time into measurable units. But Pythagoras proposed something far more radical, that musical relationships could be expressed as precise numerical ratios, and that these same ratios governed not just music, but the entire cosmos. Part 2. The Life and Legend of Pythagoras. Separating historical fact from legendary embellishment in the life of Pythagoras presents a genuine challenge. No writings from Pythagoras himself survive indeed. The Pythagoreans maintain strict secrecy about their teachings, and it's uncertain whether Pythagoras wrote anything at all. What we know comes from later writers, many of whom composed their accounts centuries after his death, by which time Pythagoras had become a semi-mythical figure. The ancient biographies paint a picture of an extraordinary individual. Iamblichus, writing in the 3rd century of the Common Era, describes Pythagoras as possessing almost divine wisdom. According to these accounts, he had a golden thigh, could be in 2 places at once, and remembered his previous incarnations. These obviously legendary elements tell us more about how later Pythagoreans venerated their founder than about the historical person. Yet beneath the mythology, a human figure emerges. Pythagoras appears to have been charismatic, intellectually brilliant, and organizationally gifted. He attracted a devoted following in Croton, including many from the city's political elite. His influence extended beyond philosophy into practical politics. The Pythagoreans became a powerful faction in Croton's government. This political involvement would eventually prove dangerous. The Pythagorean community maintained a hierarchical structure. New members underwent a probationary period, during which they had to remain silent, listening to Pythagoras' teachings without speaking. Those who passed this test became mathematicoi learners, who could participate in discussions and study the advanced doctrines. An outer circle of akausmatikoi listeners received a simplified version of the teachings. This organizational structure resembles both Greek mystery religions and later monastic orders. Daily life in the Pythagorean community followed regular patterns. Members rose before dawn to exercise their memories, recalling what they had learned and done the previous day. They took walks alone for contemplation, then gathered for communal study. They practiced gymnastics, took meals together, and spent evenings in group activities including musical performance. Music accompanied many activities. They used the lyre to calm passions before sleep and to awaken the mind each morning. Pythagoras himself reportedly possessed a powerful personality. He taught with authority, and his word became law within the community. Later, Pythagoreans would cite autos ephi. He himself said it as sufficient proof of any proposition. This reverence for the master's wisdom sometimes discouraged independent questioning, though it also helped preserve and transmit the teachings through generations. The relationship between Pythagoras and his students appears to have been intense. Iamb. Lycus describes how Pythagoras could discern each person's character through observing their walk, their laughter, their mannerisms. He supposedly tailored instruction to individual temperaments, recognizing that different souls required different approaches to wisdom. Some students needed encouragement, others needed restraint. Music figured prominently in these individual treatments. Pythagoras reportedly prescribed specific musical modes and melodies as medicine for different psychological conditions. Women participated in the Pythagorean community, a remarkable feature for ancient Greece. Theano, said to be Pythagoras' wife, became a noted philosopher herself, authoring works on mathematics and virtue. Other women, Erignote, Damo, Maya, appear in the historical record as Pythagorean philosophers. This inclusion of women as intellectual equals distinguished the Pythagoreans from most Greek philosophical schools. The community prospered for several decades. Pythagorean influence spread to other cities in Magna Graecia, but political opposition grew. Around 510 before the Common Era, an anti-Pythagorean faction led by a man named Cylon instigated violence against the community. Accounts differ on the details. Some say Pythagoreans were trapped in a building that was set ablaze. Others describe a general persecution. Pythagoras himself may have died in this violence, or he may have fled to Metapontum, another Greek city in southern Italy, where tradition places his death around 490 before the Common Era. Despite this persecution, Pythagoreanism survived. Students carried the teachings to other cities. New communities formed. The philosophical school continued for centuries, evolving and adapting. Later, Pythagoreans included Philolaus, who first published previously secret doctrines, and Archytas of Tarentum, a mathematician, philosopher, and statesman, who befriended Plato and influenced the development of Plato's philosophy. The story of Pythagoras' fundamental discovery has been told for 25 centuries, though, like much of his biography, it blends history with legend. According to tradition, Pythagoras was walking past a blacksmith's shop when he noticed that hammers of different weights produced different pitches when struck against the anvil. Intrigued, he investigated further and discovered that the relationship between the weights followed simple numerical ratios. A hammer twice as heavy as another produced a pitch 1 octave lower. This story, charming as it is, presents physical impossibilities. The physics of hammers doesn't actually work this way. But the legend contains an important truth. Pythagoras, or his early followers, discovered that musical intervals correspond to simple numerical ratios, and they made this discovery through systematic experimentation. The tool they used was the monochord, a single string stretched over a resonating box with a movable bridge that could divide the string at any point. Imagine the monochord, a wooden box, perhaps the length of your forearm, with a single string stretched tight across it. Pluck the string, and it sounds a note. Now place a bridge, exactly halfway along the string's length, dividing it in 2 equal parts. Pluck either half, and you hear a note 1 octave higher than the full string. This is the ratio of 2 to 1, the octave. Play both sounds together, and they blend perfectly. They sound so similar that we give them the same letter name. This was the first great Pythagorean discovery. The octave corresponds to the ratio of 2 to 1. Now move the bridge to 1/3 of the string's length from the end. Pluck the longer portion 2/3 of the total length, and you hear a pitch, a perfect fifth, above the fundamental. This is the ratio of 3 to 2. In modern terms, if the full string plays a C, the 2/3 length plays a G above it. This interval, the perfect fifth, is the foundation of musical harmony. It sounds consonant, pleasing, stable. Play C and G together, and they support each other beautifully. Next, position the bridge 1/4 of the way along the string. The longer portion 3/4 of the total length produces a pitch, a perfect fourth above the fundamental. This is the ratio of 4 to 3. If our fundamental is C, this gives us F above it. Like the fifth, the fourth sounds consonant and restful. These 3 ratios, 2 to 1, 3 to 2, and 4 to 3, became the foundation of Pythagorean music theory. They're formed by the numbers 1, 2, 3, and 4. Add these numbers together. 1 plus 2 plus 3 plus 4 equals 10. The Pythagoreans regarded 10 as the perfect number, the tetractes the source of all harmony. They took oaths by the tetractes. They saw in these 4 numbers and their ratios nothing less than the mathematical structure of musical beauty. The experimental method Pythagoras employed was revolutionary. He didn't rely on tradition or subjective impression. He measured, he calculated, he discovered that what the ear perceives as beautiful, harmonious, and consonant corresponds to simple mathematical ratios. Beauty, it seemed, had a numerical structure. This discovery had profound philosophical implications. The Greeks already recognized several musical intervals. They knew the octave, the diapason, meaning through all. They knew the fifth, the diapente, through 5, counting inclusively from the first note. They knew the fourth, the diatessaron, through 4. But Pythagoras revealed the mathematical relationships underlying these intervals. He showed that music was not arbitrary, but followed rational, discoverable principles. The monochord became the fundamental tool of ancient music theory. Scholars used it for centuries to demonstrate relationships between pitches, to tune instruments, to teach students. Ptolemy, the 2nd century astronomer and music theorist, devoted extensive discussion to the monochord. Boethius, writing in the 6th century of the Common Era, described it in detail for medieval readers. The instrument remained important in European music theory well into the Renaissance. But the Pythagorean discovery extended beyond merely identifying ratios. The Pythagoreans developed a complete system of tuning based on these ratios. Starting from a fundamental pitch, they built up a scale by stacking perfect fifths, move up a fifth from C to G, move up another fifth from G to D. Continue this process, D to A to E to B to F sharp. This produces what we now call Pythagorean tuning, a system that dominated Western music for over 1,000 years. Pythagorean tuning has distinctive characteristics. The fifths are pure mathematically perfect because they're all tuned to the ratio of 3 to 2. The fourths are likewise pure, but other intervals become complex. The major third in Pythagorean tuning is slightly wider than in modern equal temperament, giving it a bright, ringing quality. Some intervals, the Pythagorean comma, don't quite close the circle when you try to return to your starting point after 12 fifths. These mathematical complexities fascinated theorists for centuries and eventually led to alternative tuning systems. The philosophical implications of this discovery cannot be overstated. Pythagoras had demonstrated that the human sense of beauty has a rational basis. What sounds good isn't merely cultural preference or subjective taste, it reflects objective mathematical relationships. This suggested that reason, not emotion or tradition, should guide our understanding of music. More broadly, it suggested that mathematics might be the key to understanding all of reality. For Pythagoras and his followers, the discovery of musical ratios pointed toward a stunning conclusion. Numbers are the fundamental reality of the universe. Everything that exists, they believed, is essentially numerical. Physical objects are arrangements of numbers. Qualities like beauty, justice, and harmony are numerical relationships. Even the human soul has a numerical structure. This worldview, sometimes called Pythagorean number philosophy, represented a radical departure from earlier Greek thought. The Milesian philosophers had sought a material principle: water, air, the infinite. Pythagoras proposed that the ultimate reality was not material but mathematical. Numbers don't exist as physical things you can touch or see, yet they determine how physical things behave. This insight would influence Western philosophy for millennia. The Pythagoreans developed elaborate number symbolism. 1 represented unity, the source from which all numbers arise. 2 represented division, the first departure from unity, associated with opinion and the material world. 3 was the first truly complete number, having beginning, middle, and end. 4 represented justice and solid physical reality. Think of the 4 elements, the 4 seasons, the square's 4 corners. 5 symbolized marriage, the union of the first even and odd numbers after 1. Geometric figures possessed numerical significance. The triangle, formed by 3 points, represented harmony. The square, with 4 equal sides, represented stability and justice. The pentagon, with 5 points, became the Pythagorean symbol, used as a sign of recognition among members of the community. These geometric forms weren't merely abstract concepts, but visible manifestations of numerical reality. The Pythagoreans distinguished odd and even numbers, attributing to them different properties and associations. Odd numbers were masculine, associated with limitation and form. Even numbers were feminine, associated with the unlimited and formless. This gendered number symbolism, while problematic from a modern perspective, shows how the Pythagoreans sought to find numerical patterns in all aspects of existence. Certain numbers held special significance. We've already encountered 10, the tetractys, sum of 1, 2, 3, and 4. 7 was sacred. There are 7 planets visible to the naked eye, 7 strings on the Greek lyre, 12 organized time, 12 months, 12 hours of day and night. These weren't arbitrary associations, but reflected what Pythagoreans saw as the numerical structure woven into reality itself. The discovery of musical ratios provided concrete evidence for this number philosophy. Here was something everyone could experience. Pluck a string at its halfway point, and it sounds an octave higher. Divide it in 3:2 ratio, and you hear a perfect fifth. The numerical relationships weren't imposed by human convention, but discovered in nature. The universe, it seemed, spoke in the language of mathematics. This insight would prove immensely influential. Plato, though not himself a Pythagorean, absorbed these ideas and incorporated them into his philosophy. His famous myth of at the conclusion of the Republic describes a celestial spindle with 8 whorls, each producing a musical tone, a direct reference to Pythagorean cosmic music. His dialogue, Timaeus, presents the creation of the world's soul according to musical ratios. Through Plato, Pythagorean ideas entered the mainstream of Western philosophy. Part 3. The Music of the Spheres, Cosmic Harmony. From the discovery that musical intervals correspond to mathematical ratios, Pythagoras made an extraordinary leap of imagination. If music follows mathematical laws, and if mathematics is the fundamental principle of reality, then perhaps the cosmos itself is musical. This idea that the universe produces a harmony inaudible to human ears became known as the music of the spheres, one of the most beautiful and influential concepts in Western thought. To understand this idea, we must understand how the Pythagoreans conceived the cosmos. They believed the earth spherical and placed it at the center of the universe. Around the earth revolved 7 celestial bodies: the moon, Mercury, Venus, the sun, Mars, Jupiter, and Saturn. Beyond these planets lay the sphere of the fixed stars. Each celestial body moved in a circular orbit, and these motions, the Pythagoreans proposed, generated tones. The reasoning went something like this. On Earth, any object moving through the air creates sound, the whistle of an arrow, the rush of wind. The planets, in their motions through the heavens, must likewise create sounds. But these sounds aren't random noise. The planets move with mathematical precision. Their speeds relate to one another according to numerical ratios. Therefore, the sounds they produce must form a cosmic harmony, a music far more perfect than any earthly composition. The Pythagoreans worked out an elaborate correspondence between planetary motions and musical intervals. Though accounts vary in details, the basic principle remained constant. The faster a planet moves, the higher its pitch. The moon, closest to Earth and moving most rapidly, produces a high tone. Saturn, most distant and slowest, produces a low tone. The spacing between planets corresponds to the musical ratios Pythagoras had discovered with the monochord. Some sources describe 7 planetary tones producing a complete harmonic scale. Others add the sphere of fixed stars as an 8th tone, completing an octave. Later versions included 9 or 10 celestial bodies, sometimes even more complex arrangements. The specific details mattered less than the fundamental concept. The heavens are a musical instrument, the cosmos a symphony. This raises an obvious question. If the planets sing, why don't we hear them? The Pythagorean answer was sophisticated. We don't hear the music of the spheres, they explained, because we've been exposed to it since birth. Like people living beside a loud waterfall who cease to notice the sound, we're so immersed in cosmic harmony that we can't distinguish it from silence. Or perhaps the explanation is more metaphysical. These celestial tones exist on a level beyond physical hearing, perceptible only to souls properly attuned through philosophical study and virtuous living. Some legends claim that Pythagoras himself could hear the celestial music. His spiritual refinement and mathematical insight had purified his soul to the point where he could perceive what remained hidden to others. This claim, whether historical or legendary, illustrates how the Pythagoreans saw philosophy as a progressive refinement of the soul toward higher understanding. The music of the spheres wasn't merely poetic metaphor for the Pythagoreans. They believed this cosmic harmony was real, physical, and fundamentally important. The celestial music maintained cosmic order. The mathematical ratios governing planetary motions determined the structure of the universe. Earthly music, when properly composed according to Pythagorean ratios, echoed this cosmic perfection and could therefore influence the human soul. This belief had practical implications. If earthly music participates in cosmic harmony, then musical education becomes essential to moral development. By learning to recognize proper harmonies, the soul aligns itself with cosmic order. Conversely, improper music, music that violates mathematical relationships, disturbs the soul and leads to moral degradation. This concern about music's ethical effects would persist throughout Western history, from Plato's restrictions on musical modes in the Republic to debates about popular music in our own time. The Pythagoreans developed the concept of harmonia, a term we translate as harmony, but which meant something broader to them. Harmonia referred to the proper fitting together of disparate elements into a unified whole. In music, it meant the combination of different pitches into consonant intervals. In the cosmos, it meant the ordered arrangement of planets. In the soul, it meant the balanced relationship between reason, emotion, and appetite. In society, it meant justice, each person performing their proper role. All these forms of harmony shared the same mathematical structure. This understanding of harmony as universal principle explains why Pythagoreans regarded music as therapeutic. If the soul becomes disordered, if passions overwhelm reason, if appetites exceed proper bounds, musical therapy can restore harmonic balance. Just as a lyre player tightens or loosens strings to achieve proper tuning, carefully chosen music adjusts the tensions in the soul, bringing it back into harmony with cosmic order. Nicomachus of Gerasa, a Pythagorean writing in the 1st century of the Common Era, preserves stories about Pythagoras using music medicinally. According to these accounts, Pythagoras once encountered a young man in a jealous rage, preparing to set fire to his rival's house. Pythagoras instructed nearby musicians to change their tune from a frenzied Phrygian mode to a calm, spondaic rhythm. The young man immediately regained control of his passions and went home peacefully. Whether historically accurate or not, such stories illustrate the Pythagorean belief in music's power to affect human behavior. The same principle extended to music's use in education. The Pythagoreans began and ended each day with musical exercises. Morning music awakened the mind and prepared it for study. Evening music calmed the soul and prepared for restful sleep. During the day, they used different musical modes for different purposes: stimulating modes for exercise, contemplative modes for study, soothing modes for meals. This systematic use of music as a tool for spiritual development became a model for later philosophical schools. The Pythagorean vision of cosmic music captured imaginations across centuries and cultures. Even as the specific astronomical model changed, the underlying idea that the universe possesses a mathematical harmonic structure continued to inspire scientists, philosophers, and artists. Plato, though not himself a Pythagorean, absorbed and transmitted many Pythagorean ideas. In the Timaeus, his cosmological dialogue, Plato describes how the divine craftsman created the world's soul by mixing being, sameness, and difference in proportions corresponding to musical ratios. The creator divides this mixture according to the ratios of the octave, 2:1, the fifth, 3:2, and the fourth, 4:3. The world's soul thus has a fundamentally musical structure. When we contemplate mathematics and music, Plato suggests, we're bringing our individual souls into resonance with the soul of the cosmos. Plato's Republic discusses music education at length, emphasizing how different musical modes affect character development. The Dorian mode promotes courage. The Phrygian mode inspires moderation. Other modes produce less desirable effects and should be restricted in the ideal city. Plato didn't invent these ideas from nothing. He was drawing on and developing Pythagorean insights about music's ethical power. Aristotle, Plato's student, took a more skeptical view of cosmic music. In his work On the Heavens, Aristotle explicitly addresses the Pythagorean claim that celestial motions produce harmony. He raises the obvious objection: why don't we hear it? The Pythagorean answer that we've grown accustomed to: the sound doesn't satisfy Aristotle. He argues instead that the heavens move without friction and therefore produce no sound. Yet even in rejecting the literal music of the spheres, Aristotle acknowledges the appeal of the concept and its mathematical elegance. Despite Aristotle's skepticism, the music of the spheres concept flourished in the Hellenistic period. Astronomical texts from Alexandria describe elaborate correspondences between planets and musical tones. Astrologers incorporated musical symbolism into their systems, associating each planet with specific modes and harmonies. The idea spread beyond Greece into Near Eastern and eventually Roman culture. The Roman statesman and philosopher Cicero transmitted Pythagorean ideas to Latin readers. In his Dream of Scipio, a literary work imagining the Roman general Scipio Africanus in the heavens, Cicero describes cosmic music. "What is this sound so loud and yet so sweet that fills my ears?" Scipio asks. His guide explains, "That is the sound which, blended together in unequal intervals but still distinctly combined in fixed proportions, is caused by the onward rush and motion of the spheres themselves." Cicero's vivid description introduced countless later readers to Pythagorean cosmology. The early Christian era saw Pythagorean ideas merge with Christian theology. Church fathers like Clement of Alexandria and Origen saw no contradiction between Greek philosophy and Christian revelation. They interpreted the Pythagorean harmonic cosmos as evidence of divine order. The mathematical ratios that govern music and planetary motion reflected the wisdom of the Creator. Music itself was a gift from God, a means of approaching divine beauty. Boethius, writing in the early 6th century, provided the most influential medieval transmission of Pythagorean music theory. His treatise De Institutione Musica on Music became the standard textbook for music education throughout the Middle Ages. Boethius explained Pythagorean ratios, described the monochord, and outlined the three types of music: musica mundana, the harmony of the cosmos; musica humana, the harmony of the human soul and body; and musica instrumentalis, the actual sounds produced by voices and instruments. This threefold division proved immensely influential. Medieval scholars studied music primarily as mathematics, not as performance. Music belonged to the quadrivium, the four mathematical arts of arithmetic, geometry, astronomy, and music. To study music meant to study ratios, proportions, and cosmic harmony. Actual musical practice, while necessary for worship and education, ranked lower than theoretical understanding. The Middle Ages elaborated extensively on music of the spheres imagery. Dante's Divine Comedy culminates in a vision of the celestial rose, with souls arranged in harmonious circles like strings on a cosmic instrument. Hildegard of Bingen, the 12th century abbess and composer we'll encounter in a future episode, received visions of divine harmony and composed music to embody celestial order. Gothic cathedrals were designed with proportions derived from musical ratios, architectural expressions of cosmic harmony. The Renaissance saw a revival of Pythagorean ideas alongside rediscovery of classical texts. Marsilio Ficino, the 15th century Florentine philosopher, translated Plato and wrote extensively about music's power to affect the soul. He practiced musical therapy, playing the lyre to treat melancholy and align his spirit with celestial harmonies. His student, Giovanni Pico della Mirandola, incorporated Pythagorean number symbolism into his attempt to synthesize all philosophical and religious traditions. Renaissance musicians debated Pythagorean tuning versus newer systems, The pure fifths of Pythagorean tuning created problems when composers wanted to use all 12 chromatic notes. Alternative tuning systems emerged, each with trade-offs between mathematical purity and practical versatility. These debates show how seriously Renaissance musicians took Pythagorean mathematical principles, even while adapting them to new musical needs. Johannes Kepler, the 17th century astronomer, represents both the culmination and transformation of Pythagorean cosmology. Kepler devoted much of his career to discovering the mathematical harmonies governing planetary motion. His book, Harmonices Mundi, The Harmony of the World, published in 1619, presents an elaborate system correlating planetary orbits with musical intervals. Kepler discovered that planets move in elliptical orbits, not perfect circles. He found that planets move faster when closer to the Sun and slower when farther away. And crucially, for our purposes, he discovered that the ratios between a planet's fastest and slowest speeds correspond to musical intervals. Earth's speeds, for instance, form roughly a semitone. Venus's speeds form only a tiny interval, almost a monotone. The outer planets have larger intervals. When Kepler plotted these on a musical staff, he found what he believed was the celestial symphony Pythagoras had proposed 2,000 years earlier. Kepler's vision was simultaneously scientific and mystical. He used precise mathematical observation, the most accurate astronomical data available in his time, to pursue an essentially Pythagorean goal, demonstrating the harmonic structure of the cosmos. Though his specific correlations didn't survive later astronomical discoveries, his work exemplifies how Pythagorean ideas continued to inspire even as astronomy became increasingly mathematical and empirical. Part 4. Pythagorean Ideas in Medieval and Renaissance Music. The practical influence of Pythagorean ideas on actual musical composition and performance deserves careful attention. While medieval theorists studied Boethius and contemplated cosmic harmony, how did these ideas actually shape the music people heard? The medieval modal system, though not created directly by Pythagoreans, reflects their emphasis on mathematical order and cosmic correspondence. The 8 medieval modes, Dorian, Hypodorean, Phrygian, Hypophrygian, Lydian, Hypolydian, Mixolydian, and Hypomixolydian, each had specific ethical and emotional associations inherited from Greek theory. Composers chose modes deliberately to convey specific affects and moral qualities, echoing the Pythagorean belief in music's power to shape character. Medieval musical notation developed partly to preserve these modal relationships accurately. The staff, with its lines and spaces representing specific pitches, emerged during the 11th and 12th centuries. This invention allowed precise transmission of melodies, ensuring that intervallic relationships, the mathematical ratios Pythagoras had discovered, remained constant. Before notation, oral transmission risked gradual alteration. Written music, preserving exact pitches, maintained the mathematical purity Pythagoreans valued. The development of polyphony, multiple melodic lines, sounding simultaneously, raised new questions about consonance and dissonance. Medieval theorists, following Pythagorean principles, classified intervals as perfect or imperfect. Perfect consonances, the octave, fifth, and fourth, corresponded to simple ratios, 2:1, 3:2, 4:3. Imperfect consonances, thirds and sixths, had more complex ratios and were treated with more care. Dissonances, seconds, sevenths, tritones, violated simple ratios and required careful resolution. These weren't arbitrary aesthetic preferences. Medieval musicians believed they were working with objective mathematical relationships that reflected cosmic order. To end a phrase on a perfect consonance brought the music into alignment with universal harmony. To resolve a dissonance according to proper voice-leading rules maintained the mathematical relationships that govern both music and cosmos. The mathematics of counterpoint, the rules governing how melodic lines combine, developed from Pythagorean foundations. When two voices move together, certain combinations produce consonance, others dissonance. Renaissance theorists like Gioseffo Zarlino in the 16th century wrote elaborate treatises explaining these combinations through mathematics. Zarlino expanded the Pythagorean ratios to include more complex ones, allowing for richer harmonies while maintaining mathematical principles. The Renaissance rediscovery of ancient texts included Pythagorean works. Scholars could now read Plato's Timaeus in Greek rather than medieval Latin translations. They encountered Ptolemy's discussions of musical ratios and tuning systems. This renewed engagement with classical sources inspired attempts to recreate ancient Greek music and led to the invention of new instruments designed according to Pythagorean principles. The Florentine Camerata, a group of intellectuals meeting in the late 16th century, deliberately sought to revive what they believed was ancient Greek musical practice. They studied Pythagorean texts, debated tuning systems, and eventually invented opera as an attempt to recreate the union of music and drama they imagined characterized Greek theater. Though their understanding of ancient music was imperfect, their Pythagorean-inspired experiments led to one of the most important developments in Western music history. Musical instrument construction reflected Pythagorean mathematics. Organ builders calculated pipe lengths using ratios to ensure proper intervals. Lute makers positioned frets according to mathematical formulas derived from Pythagorean tuning. Harpsichord builders adjusted string lengths and tensions following these same principles. The physical instruments people played embodied Pythagorean mathematical relationships. Tuning practices reveal tensions between Pythagorean mathematical purity and practical musical needs. Pythagorean tuning, based on stacking pure fifths, works beautifully for some musical situations but creates problems in others. The major thirds are noticeably sharp compared to modern equal temperament. If you tune 12 consecutive fifths up from a starting note, you don't arrive exactly at a note 7 octaves higher. There's a small discrepancy called the Pythagorean comma. Musicians and theorists struggled with these issues for centuries, developing various compromise tunings that preserved as much mathematical purity as possible while allowing for practical music making. Equal temperament, which eventually became standard in Western music, represents a departure from pure Pythagorean ratios. In equal temperament, no intervals except the octave are mathematically pure, all are slightly compromised to allow modulation to any key. Yet even this system traces back to Pythagorean foundations. The decision to divide the octave into 12 equal parts, while creating tempered fifths and thirds, still rests on understanding intervals as mathematical relationships that can be precisely measured and adjusted. The Pythagorean project of finding mathematical order in music continues even in this compromise system. Understanding how ancient and medieval musicians actually performed provides insight into how Pythagorean ideas manifested in sound. We must piece together this understanding from fragmented evidence, surviving instruments, theoretical treatises, literary descriptions, artistic representations, and the few notated pieces that preserve actual melodies. The Greek lyre, central to Pythagorean demonstrations, typically had 7 strings tuned to a diatonic scale. Evidence suggests Greek musicians tuned these strings precisely, using the monochord method to ensure accurate fifths and fourths. Performers would occasionally adjust tuning between pieces, retightening or loosening strings to accommodate different modes. This practice reflects the Pythagorean emphasis on exact mathematical relationships. Greek music was primarily melodic rather than harmonic. Instruments typically doubled the vocal line or played heterophony slight variations on the same melody. This differs markedly from later Western music, where harmony became paramount. Yet even monophonic music follows Pythagorean principles. The intervals between successive notes in a melody correspond to mathematical ratios. A melody rising by a perfect fourth follows the 4:3 ratio, whether those notes sound simultaneously or in sequence. Rhythm in ancient Greek music related to poetic meter. Long and short syllables in poetry corresponded to long and short musical durations. These durational relationships could be expressed mathematically, a long syllable might be twice the length of a short syllable, a ratio of 2 to 1, the same ratio as the octave. This parallel between melodic intervals and rhythmic proportions reflects the Pythagorean vision of pervasive mathematical order. Medieval monophonic chant, Gregorian chant, and related traditions continued this emphasis on melodic purity and mathematical proportion. Chant melodies move by steps and small intervals, emphasizing the octave, fifth, and fourth. The careful preservation of these interval relationships through notation reflects ongoing Pythagorean influence. When monks sang the office hours day after day, year after year, they participated in a tradition of ordered, proportioned music, stretching back to Pythagoras. The development of organum, early polyphony, where a second voice accompanies the chant melody, began with strict parallel motion at the interval of a perfect fourth or fifth. Later, voices moved more independently, but still emphasized perfect consonances at important cadence points. This practice embodies Pythagorean principles. The perfect intervals, corresponding to simple ratios, provide stability and resolution, while other intervals create motion and tension. Medieval and Renaissance musicians thought carefully about tessitura, the range in which each voice sounds. Theorists wrote of the proper proportions between voices, using mathematical ratios to determine ideal spacing. The relationship between soprano and alto, for instance, should mirror the relationship between alto and tenor. These weren't arbitrary conventions, but reflected beliefs about cosmic harmony manifesting in musical performance. Tempo and expression present challenges in understanding historical performance. Ancient and medieval sources rarely specify tempo precisely. However, the association of music with cosmic order suggests a certain regularity and inevitability in performance. Music shouldn't sound rushed or arbitrary, but should unfold with the mathematical necessity of planetary motion. This doesn't mean mechanical rigidity. Subtle variations in timing can enhance musical expression, but suggests an underlying sense of order and proportion. The use of instruments offers another window into performance practice. Greek instruments included the lyre, the kithara, a larger lyre, the aulos, double reed instrument, and various percussion. Medieval Europe added the organ, the vielle, bowed string instrument, the harp, and various wind and percussion instruments. Renaissance instruments expanded this palette further. Each instrument had characteristic timbres and capabilities, but all were tuned according to Pythagorean or related mathematical systems. Vocal production in ancient and medieval music likely differed from modern operatic singing. Evidence suggests a lighter, more speech-like delivery for much medieval music. Chant probably used a relatively pure tone without much vibrato. Troubadour songs and similar secular music may have been more speech-like still, with clear diction taking precedence over pure vocal beauty. Yet, even in these styles, careful attention to pitch to the mathematical relationships between notes remained essential. The concept of musica ficta, the practice of adding chromatic alterations not written in the notation, shows how performers balanced mathematical principles with practical needs. Medieval notation didn't always include the sharps and flats performers added. These alterations often aimed to avoid tritones, the augmented fourth, with an uncomfortable mathematical ratio, or to create smoother melodic lines. Performers made these decisions based on training in Pythagorean principles, adjusting pitches to maintain proper mathematical relationships. Beyond theory and abstract mathematics, how did ordinary people experience music shaped by Pythagorean ideas? What did it feel like to hear music conceived as embodying cosmic order? For the Greeks, music permeated daily life. Symposia drinking parties where educated men gathered featured musical performance. Poetry recitals included musical accompaniment. Religious festivals centered on choral performances. Athletic games included musical competitions. Theater combined drama, music, and dance. In all these contexts, participants experienced music as ordered, proportioned, and meaningful. The ancient Greek attitude toward music combined pleasure with seriousness. Music was entertaining, certainly, but it was also formative. Parents carefully chose music teachers for their children, understanding that musical education shaped character. Young men learning the lyre didn't merely acquire a social accomplishment, they were training their souls in harmony and proportion. This understanding elevated the status of music, while also creating anxiety about improper music's corrupting influence. Religious contexts gave music special significance. Hymns to Apollo at Delphi, paeans sung at festivals, dithyrambs in honor of Dionysus, all served ritual functions. But beyond mere accompaniment to ceremony, Greeks believed this music participated in divine harmony. When the chorus sang at a dramatic festival, they weren't just entertaining the audience, they were manifesting cosmic order in sound, creating a momentary alignment between human community and universal harmony. Medieval Christians inherited and adapted these ideas. Monastic communities structured their entire day around sung prayer, the divine office, with its 8 canonical hours. Monks rose in the night to sing matins, sang lauds at dawn, prime at the first hour, and continued through the day to compline before sleep. This constant cycle of sung prayer wasn't merely devotional practice, it was participation in eternal worship. Medieval theology imagined the angels singing perpetual praise in heaven. When monks sang the office, they believed they were joining their voices to this celestial choir, bringing earth into harmony with heaven. Cathedral worship featured more elaborate music. The great Gothic cathedrals, designed with proportions derived from musical ratios, created spaces where music resonated magnificently. The development of polyphony meant that congregations could hear multiple melodic lines weaving together in complex mathematical relationships. The architecture itself embodied Pythagorean ratios, the proportions of nave to aisle, the heights of arches, the spacing of columns, all reflected musical mathematics. When polyphonic music sounded in such a space, the building and the music together manifested cosmic harmony in stone and sound. Secular medieval music brought similar ideas into daily life. Troubadours and minnesingers, whom we'll explore in future episodes, composed love songs using modal scales and mathematical proportion. Court dancing followed measured steps and regular rhythms. Even work songs and folk music, though less formally structured, participated in this culture of ordered, proportioned sound. The Renaissance saw increasing sophistication in musical practice alongside continued reverence for Pythagorean principles. As polyphonic complexity increased, composers faced greater challenges in balancing mathematical order with musical expressiveness. A 4-voice motet by Josquin des Prez or Palestrina, which we'll study in upcoming episodes, contains intricate mathematical relationships between voices while also creating profound emotional effects. The mathematics serves the expression rather than constraining it. Domestic music making flourished during the Renaissance. Educated families owned instruments, lutes, viols, keyboards. They gathered to sing madrigals and play consort music. These amateur musicians didn't necessarily understand the Pythagorean theory underlying their music, but they had been trained in a musical culture that valued proportion, consonance, and ordered beauty. The experience of making music together, creating harmonies in real time, gave them direct participation in the cosmic harmony Pythagoras had described. For individuals throughout these centuries, music offered both pleasure and meaning. A beautiful melody provided immediate enjoyment, but it also connected the listener to something transcendent. The mathematical perfection of a consonant interval, the inevitable resolution of a dissonance, the satisfying conclusion of a well-proportioned phrase. These weren't just aesthetic satisfactions, but glimpses of cosmic order. Music, properly understood and properly performed, made audible the mathematical harmonies governing the universe. Part 5. Synthesis, the enduring power of mathematical beauty. As we near the end of our exploration of Pythagoras and the music of the spheres, let's step back to consider the broader significance of these ideas. What can we, 25 centuries after Pythagoras, take from his vision of music as mathematical harmony. First, we should acknowledge what Pythagoras got right. Musical intervals do correspond to simple mathematical ratios. A string divided in half does sound an octave higher. These ratios aren't cultural conventions but physical facts about how sound waves interact. Pythagoras discovered something objectively true about the natural world through systematic experimentation. His methods, careful observation, measurement, reproducible experiments, anticipated the scientific method that would fully flower 2,000 years later. Second, Pythagoras' insight that mathematics describes natural phenomena has proven profoundly correct. Modern physics uses mathematics to describe everything from subatomic particles to the structure of space-time. The universe does, in a real sense, operate according to mathematical principles. Pythagoras' intuition that number is fundamental to reality finds sophisticated expression in contemporary theoretical physics, where some scientists argue that the universe is fundamentally mathematical in nature. Third, the connection Pythagoras proposed between beauty and mathematical order continues to resonate. We still find elegant mathematical proofs beautiful. Symmetry in art and architecture pleases the eye partly because of its underlying mathematical regularity. While beauty involves more than mathematics alone, there does seem to be something true in the Pythagorean recognition that our aesthetic sense responds to proportion and order. At the same time, we must acknowledge what Pythagoras got wrong, or at least what later developments have complicated. The literal music of the spheres, the idea that planetary motions produce audible harmony, doesn't survive modern astronomy. Planets move through vacuum, which transmits no sound. The geocentric model Pythagoras assumed, with Earth at the center and planets moving in circular orbits, has given way to a heliocentric model with elliptical orbits, and eventually to a model of the universe vastly larger and stranger than ancient Greeks imagined. Yet even here, something of the Pythagorean vision persists. Modern astrophysics finds mathematical relationships governing celestial mechanics. Planetary orbital periods relate to their distances from the Sun according to Kepler's laws, which are mathematical formulas. The universe does operate according to equations, even if those equations don't produce literal music. In a metaphorical sense, Pythagoras wasn't entirely wrong. There is a kind of cosmic harmony, expressed not in audible tones but in mathematical laws. The Pythagorean approach to music theory dominated Western thought for over 2,000 years. The idea that pure mathematical ratios produce the best consonances shaped tuning systems, compositional practice, and instrument construction through the Renaissance. When European music eventually moved toward equal temperament, abandoning pure Pythagorean ratios for practical compromise, this represented a significant philosophical shift, a willingness to prioritize practical utility over mathematical purity. Yet we shouldn't overstate this shift. Equal temperament still rests on mathematical principles. The decision to divide the octave into 12 equal semitones is a mathematical one, even if the resulting intervals are tempered rather than pure. Modern music theory continues to use mathematics extensively, analyzing harmonic relationships, describing rhythmic proportions, calculating acoustic properties. The Pythagorean project of understanding music mathematically remains very much alive. The ethical dimension of Pythagorean music theory, the belief that music affects character, and that proper music promotes virtue, has waxed and waned through history. Medieval and Renaissance thinkers took these ideas seriously. The Enlightenment tended toward skepticism about music's moral power. Romanticism emphasized emotional expression over mathematical order. Yet debates about music's social and moral effects never entirely disappeared. We still ask whether certain kinds of music promote undesirable attitudes or behaviors, whether music education contributes to moral development, whether musical taste reflects character. These questions echo Pythagorean concerns, even when we approach them from different theoretical perspectives. The mystical dimension of Pythagoreanism, the belief in reincarnation, the secret doctrines, the spiritual exercises has seemed increasingly foreign to modern secular culture. Yet here too we find persistence and transformation. The idea that contemplation of mathematical beauty brings spiritual enlightenment survives in various forms. The practice of using music therapeutically, which Pythagoreans pioneered, continues in modern music therapy. The sense that music connects us to something transcendent, that it offers glimpses of a higher reality, remains common even among people with no religious commitments. What of the music of the spheres, specifically? Though we no longer believe in literal celestial harmony, the metaphor retains power. Composers from medieval times to the present have created pieces inspired by cosmic themes. Holst's Planet Suite, though not Pythagorean in any technical sense, reflects the ancient impulse to imagine planets as musical. John Adams's Harmonium, Philip Glass's Einstein on the Beach, Caroline Stockhausen's Clang, all engage with ideas of cosmic order and musical metaphors for the universe's structure. Contemporary physics has even found something remarkably like music of the spheres in unexpected places. String theory, one approach to quantum gravity, proposes that fundamental particles are actually tiny vibrating strings. Different vibration patterns correspond to different particles, electrons, quarks, photons. In this view, the universe, at its most fundamental level, consists of vibrations, a literal music of tiny strings. Though these vibrations don't produce audible sound and aren't musical in the ordinary sense, the parallel to Pythagorean ideas is striking. Once again, at the deepest level of reality, we find vibration and mathematics intertwined. The Pythagorean legacy in Western music is incalculable. The very concept of music theory, the idea that music can be studied systematically, that it follows discoverable principles, that it can be taught through rational methods, stems from Pythagoras. Before Pythagoras, music was learned through apprenticeship, transmitted through tradition, understood as craft rather than science. After Pythagoras, music became a subject for philosophical investigation, mathematical analysis, and theoretical speculation. This theoretical approach has benefits and drawbacks. On one hand, music theory has enabled sophisticated analysis, supported music education, and helped composers understand their craft. On the other hand, excessive emphasis on theory can make music seem cold or mechanical, can create barriers between theoretical understanding and practical music making, can privilege certain kinds of music, those easily analyzed using existing theoretical tools over others. Balancing theoretical rigor with musical spontaneity, mathematical precision with emotional expression, remains an ongoing challenge. Pythagoras' most fundamental insight, that there's an objective basis to musical beauty, continues to generate debate. Some argue that musical preferences are entirely cultural, that what sounds good varies completely across societies and historical periods. Others point to apparently universal responses to certain musical features, consonant intervals, sound stable across cultures, regular rhythms facilitate movement and dance. The truth likely lies between these extremes. Music is both culturally shaped and grounded in acoustic and neurological realities that transcend culture. Pythagoras' discovery that simple ratios produce consonance points toward one such transcultural reality, even as we recognize that music involves much more than intervals alone. As this episode draws toward its close, I want to suggest ways you might experience the ideas we've explored. While we can't hear the literal music of the spheres, we can listen to music shaped by Pythagorean thinking and appreciate the mathematical beauty Pythagoras discovered. Start with the simplest experience. Listen carefully to the interval of the octave. You might sing a note and then sing an octave above it. Notice how similar these two pitches sound, how they seem to be the same note at different heights. This is the 2-to-1 ratio Pythagoras discovered. Let yourself really hear this relationship. The mathematical simplicity of 2-to-1 expresses itself as this profound musical similarity. Next, listen to perfect fifths. Many familiar melodies begin with a fifth, the opening of Twinkle, Twinkle, Little Star, for instance. The 3:2 ratio manifests as this bright, open, stable sound. Medieval and Renaissance music emphasizes fifths heavily, reflecting Pythagorean principles. Listen to a piece of early organum, the early form of polyphony, where voices move mostly in parallel fifths. You can find recordings of Léonin or Perrotin, composers from 12th century Notre Dame in Paris. Hear how the parallel fifths create a spacious, hollow quality, very different from later harmony but beautiful in its mathematical simplicity. For a more elaborate experience of Pythagorean principles, explore medieval plain chant. Gregorian chant moves by careful intervals within modal scales. Listen to a recording of the Kyrie from a medieval mass, or the Salve Regina antiphon. Notice the modal quality, the way the melody revolves around specific pitches, the absence of harmony in our modern sense. This is monophonic music, single-line melody, but it's music that carefully observes the mathematical relationships Pythagoras discovered. Renaissance polyphony takes Pythagorean ideas further. A mass by Josquin des Prez, or a motet by Palestrina, contains intricate mathematical relationships between voices. Each voice follows its own mathematically proportioned line, and the voices combine according to rules derived ultimately from Pythagorean ratios. Listen to Palestrina's Missa Papae Marcelli, or Josquin's Ave Maria, Virgo Serena. Let yourself hear both the individual melodic lines and the way they combine into larger harmonies. If you're inclined toward instrumental music, the solo lute music of the Renaissance offers a quieter way to appreciate these ideas. Lute tuning followed Pythagorean principles, and lute compositions explore modal harmonies and careful mathematical proportions. John Dowland's Lacrimae or Francesco da Milano's Ricercars provide beautiful examples. The intimate sound of the lute, its gentle resonance, makes it ideal for contemplative listening. Bach represents a culmination of mathematical music in the Baroque era. Though Bach lived over 2,000 years after Pythagoras, he was deeply influenced by mathematical thinking about music. His well-tempered clavier, which we'll explore in detail in future episodes, presents preludes and fugues in every major and minor key, demonstrating the possibilities of systematic organization. His art of fugue explores complex mathematical relationships between melodic lines. Even his more accessible works, the cello suites, the violin sonatas, and partitas, embody sophisticated mathematical structures. Listen to any of these works with an awareness of their mathematical underpinnings. For a modern engagement with cosmic music themes, explore Holst's orchestral suite, The Planets. Though Holst wasn't attempting to recreate Pythagorean theory, his musical portraits of planets reflect the ancient impulse to imagine celestial bodies through sound. Each movement has distinctive character. Mars brings warlike aggression, Venus brings serenity, Jupiter brings jollity. Holst's orchestration creates a sense of cosmic vastness that echoes, in its own way, Pythagorean visions of celestial harmony. If you're drawn to more contemporary music, seek out Arvo Pärt's work. Pärt developed a compositional technique he calls tintinnabuli, which creates music of remarkable simplicity and purity. His Spiegel, I Am Spiegel, or Furalina use minimal materials, simple scales, spare textures to create meditative soundscapes. While not explicitly Pythagorean, Pärt's music shares the Pythagorean aesthetic of mathematical clarity and spiritual depth. Another contemporary composer worth exploring is Gavin Bryars. His work, The Sinking of the Titanic, layers musical materials in ways that create gradually shifting harmonies. The effect is hypnotic and contemplative, suggesting vast time spans and cosmic perspectives. Bryars isn't recreating ancient music, but his approach to time and harmony resonates with Pythagorean ideas about mathematical order and cosmic structure. For a direct engagement with historical performance practice, seek out ensembles specializing in early music played on period instruments. Ensemble Organum, under Marcel Pérez, has recorded extensive medieval repertoire. The Dufay Collective explores medieval instrumental music. Anonymous 4 recorded beautiful medieval and Renaissance vocal music. These ensembles work to recreate not just the notes but the sound world of earlier eras, using historically appropriate performance techniques. Don't neglect the experience of making music yourself. If you have access to an instrument, even just your voice, try exploring intervals. Sing a note and then its octave. Sing a note and its fifth. If you have a guitar or a similar stringed instrument, try the Pythagorean experiment. Play an open string, then touch it exactly at its midpoint while plucking. You'll hear the octave. Try dividing the string at different points and notice how different mathematical divisions create different intervals. This direct physical experience brings Pythagorean discoveries alive in a way that merely reading about them cannot. Finally, simply listen with awareness. Whatever music you encounter, notice intervals. Pay attention to consonance and dissonance. Observe how melodies move and how harmonies resolve. You don't need to analyze formally or understand music theory deeply. Just bring conscious attention to the mathematical relationships that underlie musical beauty. This kind of listening transforms music from background sound into an opportunity for contemplation. And so we reach the end of our journey through Pythagorean music and cosmic harmony. We've traveled from a 6th century workshop where a philosopher discovered mathematical ratios to the heavens where planets were imagined singing. We've traced these ideas through 2.5 millennia of Western thought, seeing how they shaped music theory, influenced composition, inspired philosophy, and continue to resonate today. Thank you for joining me on this exploration. I hope these ideas about music and mathematics, about cosmic harmony and earthly beauty, give you food for thought as you rest. Whether you've listened actively throughout or allowed these words to wash over you as you drift toward sleep, I'm grateful for your time. If this journey through ancient musical philosophy brought you peace or sparked your curiosity, I'd be grateful if you'd consider subscribing to The Slumbering Musicologist. Each week, we explore another chapter in the history of Western music, combining scholarly depth with a gentle pace suitable for rest and reflection. You'll find a playlist of all episodes perfect for extended listening, ideal for peaceful evenings or restful nights. New episodes arrive every Friday at 6 p.m. Greenwich Mean Time. We're moving chronologically through music history, so if you join us week by week, you'll experience the grand sweep of Western music unfolding in proper sequence. If you've enjoyed this episode, perhaps like it or leave a comment sharing your thoughts. Your engagement helps others discover these peaceful journeys through music history. Next Friday, we'll leave the philosophical world of ancient Greece and enter the practical, entertainment-focused culture of ancient Rome. We'll explore music in the Roman Empire, from grand spectacles in the Colosseum to intimate performances at private banquets, from military music to theatrical productions. Join me for Roman entertainment, music in the empire. Until then, rest well. Let the mathematical beauty of consonant intervals, the ancient vision of cosmic harmony, and the gentle melodies of period-appropriate music accompanying this episode carry you toward peaceful rest. The universe may not literally sing, but the order Pythagoras discovered in music, that deep connection between mathematics and beauty, remains as true today as it was 25 centuries ago. In recognizing that order, in appreciating those relationships, we participate in a tradition of wonder that stretches back to the ancient world and forward into whatever musical futures await. Sleep peacefully, and I'll see you next Friday.